Welcome, NLP scholars. We all know digital documents are literally everywhere: hospital, sports, bank, court, police. Really everywhere. Almost 2.5 trillion documents worldwide are available in the digital format. However, it is challenging to automatically recognize the layout and components of these unstructured digital documents, and extract meaningful information using this format. For example, the financial office would require the scanned document image after their client signed. It is then crucial to recognize and extract the form component, such as the company name, dates, or keys and values in the table. This task is widely called document layout analysis, DLA. Traditional deep learning-based DLA approaches mainly apply visual and textual features. But, it is not enough to analyze the characteristics and relations of document layout components in order to classify them. There should be two questions to solve this issue. The first question is, what would be the best aspects to represent the characteristics of different document layout components? We consider the text density as one valuable feature to distinguish different document layout components. For example, we can see that a paragraph is usually denser and contains more text than a table. Additionally, syntactic information can be another key characteristic. For example, a title usually contains only noun phrases, whereas a paragraph contains more verbs. Thus, to conduct the comprehensive learning of document properties, we capture the features of each document layout component from 4 aspects, including text density, appearance, syntactic, and semantic information. The second question is, how to represent the relation among document layout components. In addition to capturing the characteristics of document layout components, recognizing their relationships is also important for document layout understanding. For example, assume a text component is detected based on its characteristics, but it's actually more accurate to be classified as a figure caption when it's located closely above or below a figure component. However, no previous works have considered such integration of relationships for better document understanding. In this paper, we propose a novel heterogeneous graph convolutional network-based DLA model, Doc-GCN, to integrate the relative positional and structural relations between layout components. For each document page, we regard each document layout component as a node of the graph. We construct 4 different graphs, each capturing one characteristic among text density, appearance, syntactic, and semantic features. We use GCN to update the node embedding by learning from its intimate neighbors. We concatenate the learned features from all aspects to get the final document layout component representation for the classification. Previous works used faster RCNN as the basic deep learning model for DLA tasks, to process only the visual features. Some other works tried to solve the task by using only textual features with the pre-trained language models. Though some recent works tried to integrate both visual and textual features, none of them have considered other feature aspects as we did, nor the relationships between document layout components. Overall, our Doc-GCN model constructs 6 different graphs for each document page. Each document layout component is segmented by its bounding box and treated as a node in the graph. We constructed 2 graph variants for density and syntactic aspects respectively, and 1 graph for appearance and semantic aspects respectively. We applied different edge connection methods for different graphs to differently encode positional and structural relationships between document layout components. Now, let's have a look at how we construct the 4 aspect graphs. We have 2 graph variants for the text density aspect. One graph encodes the text density ratio, and the other to encode the absolute character numbers of the layout component. These 2 values are projected into the higher dimension via the positional encoding equation to get the initial node embedding. We connect each node with its 2 closest neighbors that has the smallest gap distance between their bounding boxes. The edge weight is set as the inverse gap distance to emphasize the positional relationship between closer nodes. For the appearance aspect graph, we initialize each node embedding with the visual features, which are extracted by a pre-trained faster RCNN over the cropped layout component regions. The appearance aspect graph follows the same edge connection method as the density aspect graphs. For the syntactic aspect graphs, we use the constituency parser to extract both the first level and the second level syntactic tags of the texts in each layout component, and construct 2 syntactic graph variants. We use the same positional encoding equation to get a higher dimensional embedding for each syntactic tag. For each layout component, we have a sequence of syntactic tag embedding. We pass that into a BI-LSTM model, and extract the last hidden states as its node embedding of syntactic aspect graphs. We connect every two nodes in the graph and set a binary edge value, based on the existence of the parent-child relationship, between every two layout components. We identify the layout component, at a higher structural level as the parent, of the layout component at the lower level. For example, a title is the parent of its subsequent paragraph, and a figure is the parent of its figure caption. We extract such parent-child relation between the layout components, from the document's source files following the structural parser. This is used directly for the training and validation set. But for the test set, we propose a parent-child relation prediction model, to get the parent-child relations, for our graph construction. For the semantic aspect graph, we pass the text sequences of each layout component into the pre-trained BERT, and extract the CLS token representation, as the semantic embedding of this layout component. For the edge connection, we follow the same method as for the syntactic graphs. After constructing all the graphs, we pass each graph to GCN, to update the node features, by learning and integrating information from the neighbor nodes. Then, for each aspect, we apply the node-level max pooling, over the updated node embeddings. For the appearance and semantic aspect with only one graph variant, the max pooling is applied over the updated node features and the initial node features. Finally, for each node, we have 4 ultimate features representing each aspect. These 4 different features are concatenated together as the final layout component representation. We pass this representation to a 2-layer MLP, for the final classification of the layout component type. We conducted our experiments, on 3 publicly available document layout analysis datasets, PubLayNet, FUNST, and DocBank. PubLayNet contains around 360,000 document images, and has 5 different layout component types: text, title, list, table, and figure. FUNST is a much smaller dataset, which is only 199 document pages, and 4 layout component types: header, question, answer, and other. DocBank contains 500,000 document pages, and 13 different layout component types: abstract, author, caption, date, equation, figure, footer, list, paragraph, reference, section, table, and title. We compare our model with 4 different baselines. Faster RCNN, which uses only visual features. BERT and Roberta regard the DLA task as a text classification task, by processing only textual features. Layout LM is a pre-trained model that jointly processes visual and textual features. We evaluate the model performances on F1 score. From the following result, we can see that our Doc-GCN surpasses all the baseline models on the PubLayNet dataset, and achieves huge improvement in the recognition of table, list, and figure components. This proves the success of the integration of the parent-child relationship, between layout components. Especially, for the list component, which is hard to distinguish from the text component, by considering the layout component characteristics only. Same for the FUNST dataset, our model achieves the highest performance, on all the component types compared to the other baselines. Such good performance is maintained on the DocBank dataset as well. We can see that on most component types, our Doc-GCN achieves much better performance than all the other baselines. And also achieves huge improved results on certain component types, such as caption, footer, list, title. These components can be hard to distinguish, by considering only visual and textual features, which proves the importance of capturing other characteristics of layout components, and the significance of integrating relationships in DLA task. We visualize the sample results, for the top 3 models on a document page of PubLayNet dataset. We can see that, both Roberta and Faster RCNN have wrongly recognized a text into list, whereas our Doc-GCN has accurately recognized all components. This further proves that, simply considering the semantic or visual information, is hard to distinguish the list and text, indicating the importance of capturing the structural relationships between layout components for better performance. To inspect the effectiveness of each aspect feature used in Doc-GCN, we further compare the performances, by applying different combinations of aspect features. Using only semantic or appearance features already resulted in around 96% and 88% in F1, on PubLayNet and DocBank respectively. For FUNST, using only appearance features results in 70.63% in the F1, and using only semantic features is around 10% higher. The combination of semantic and appearance features improves the F1 for all 3 datasets. Though the semantic and appearance features seem to dominate the model's performance in the DLA task, the syntactic and density features also positively contribute to the performance. We can see that the performances on all three datasets have improved, after adding syntactic and density features, which proves the utilization of both density features and syntactic features is effective for performance improvement in the DLA task. In conclusion, our Doc-GCN is the first attempt to apply heterogeneous aspects of document layout analysis. We are also the first to propose using multi-aspect graph convolutional networks for harmonizing the characteristics and relationships among document layout components. Our Doc-GCN achieves SOTA performance on three widely used DLA datasets, PubLaNet, FONST, and DocBank. We strongly hope our Doc-GCN will motivate and provide insights into the future integration of different modalities and aspects for DLA tasks.